This short video is going to very briefly talk about nutrients as an introduction to chapter 26 in your textbook. Now, last week we covered the digestive system. We took a look at how the digestive system ingests food and drink and breaks it down into individual molecules that we use as nutrients. Nutrients provide either building blocks to make molecules in your body, or they provide fuel for your cells of the body. Now, as we take a look at this introductory material, I do want to bear in mind that this is not a nutrition class. We're not going to be learning what are good nutrients and bad nutrients. However, from a dietary perspective, you do need to know the difference between essential nutrients and non-essential nutrients. And so as you read through the textbook, bear that in mind, understand which must come in the diet, which your body can synthesize on its own. Now, as we take a look at the metabolism of those molecules in your body, we're going to learn about catabolism or catabolic reactions, which break down molecules to release energy, and anabolism or anabolic reactions, which use energy to build up molecules. Now, we can combine these two processes through ATP. Large complex molecules like carbohydrates, like polysaccharides, proteins, and triglycerides can be catabolically broken down into simple molecules like glucose, amino acids, glycerol, and fatty acids. In the process, energy is released, and that energy is converting ADP into ATP. Some of the energy is released as heat, but you are able to save some as ATP. Then you're able to take those simple molecules and using that stored ATP energy, anabolically now you're able to then build larger molecules. And so cells will break down glucose to generate carbon dioxide, make ATP, use that by other cells to then make new proteins, new lipids, new carbs, what have you. Now also bear in mind the distinction of oxidation and reduction. This is the transfer of electrons. This is the energy that allows us to be able to make or use ATP energy. When a molecule undergoes oxidation, it loses electrons, it releases energy. When a molecule is reduced, it gains electrons, it gains energy. Those electrons during oxidation are released. Sometimes they directly phosphorylate ADP to ATP. Most times they do not. And so we need electron carrier molecules to transport those high energy electrons from the cytoplasm of a cell into the mitochondria, where the electron transport chain can finish the job. The two electron carriers that your body uses are NADH and FADH2. Now, when we take a look at NADH or FADH2, NADH starts out as a molecule abbreviated NAD. Now, when an NAD molecule receives this high energy electron, he also grabs a hydrogen ion, a proton, to balance out the charge, and this becomes that NADH. This is now a charged molecule. Or powered molecule, excuse me, a powered molecule. This powered molecule can now be moved into the mitochondria. The electron transport chain will then strip off the electron, throw away the hydrogen, you regenerate the NAD, and this electron is now used to make ATP. That NAD travels back out to the cytoplasm where it joins glycolysis and the citric acid cycle, and able to grab new electrons to come back this way. By the same token, you also have FAD. He'll grab 2 electrons and 2 hydrogens, and that'll generate FADH2. Same idea. He'll now be powered, travel to the mitochondria, where he will then release these electrons, allowing us to regenerate the unpowered FAD. Now, there are 6 different nutrients generated by the food you consume: carbohydrates, lipids, proteins, nucleic acids, minerals, and vitamins. You're going to be learning about each one of these as you read through the chapter. You're going to learn what the monomer building block is, the monomer nutrient form of each. In the case of carbohydrates, that'd be glucose. So all carbohydrates that you ingest, your small intestine must break them down enzymatically all the way down to the level of the monosaccharide glucose, which is then absorbed into the bloodstream and used by your cells. The storage form is glycogen. So when you eat a big meal and excess glucose is at the moment not needed, the liver will store that as glycogen for later usage. How much glycogen can your liver store? Approximately 1 day's worth of fuel. Any more than that, and your body simply will not accept more glycogen. That extra glucose will actually be converted into triglycerides and fat. Now, speaking of lipids, the monomer building block is the fatty acid, long-chain hydrocarbon. The storage form are those triglycerides, fat tissue, adipose tissue. How much? Well, unlimited. You know, every cheese tater tot you can shove down your gob hole, your body will find space to store this. So there is no limit to how much adipose tissue your body can store. Proteins, the monomer building block, are amino acids. There is not a storage form of amino acids. Your body does not store amino acids. The most you have is the plasma pool. That means that you have a number of amino acids floating around in the plasma of your blood, so that anytime a cell needs to make a protein, he looks through the plasma passing by and he grabs a little bit of this, a little bit of that, a little bit of that, connection together like Legos, and he makes a protein. So you do have the plasma pool of amino acids, but you don't have a storage form. So how much amino acids can you store? Well, the answer is a big fat 0. You can't store any. So when your cells need proteins, they're going to grab out of the plasma pool. And if you don't have the correct amino acid available, they will have to start breaking down the proteins of your body, the ones that you are using. And so when your body gets desperate enough to need amino acids to make proteins when you're incredibly starved, you're going to start breaking down your own body. Nucleic acids, monomer building block of the nucleotides. Now, you learned about these back in Bio 181. You learned about the different A, T, G, C, and U. We're not going to get back into all those elements, but I need you to simply know that the polymer storage form, as it were, is the large molecule DNA, your permanent information molecule to cells, and RNA, the temporary information molecule to cell. Minerals are inorganic nutrients required for metabolic functions. And so these are nutrients that are inorganic, they're not carbon-based. Your body is able to take these in and use them for a variety of metabolic needs. We have studied several of these in the course of A&P1 and A&P2, so this list should look very familiar. You'll be reviewing through the functions of these, be able to explain what the value of calcium and phosphate is, sodium, potassium, chloride, magnesium, iron, iodide, fluoride, be able to know what their function is. Now, the last one are the vitamins. Vitamins are organic nutrients. They are carbon-based. That means they're made by living organisms. They're required as substrates or as coenzymes. We can divide off vitamins into water-soluble and lipid-soluble vitamins. The water-soluble are the B family and vitamin C. The lipid-soluble are A, D, E, and K. You will need to know the scientific name of each one of these vitamins and the function of each one of these vitamins. Now, our next video is going to take us into catabolic reactions. That's where we're going to take these nutrients and we're going to actually burn them up to make fuel, to make ATP energy. The last 3 nutrients, the nucleic acids, the vitamins, and the minerals, are not used for fuel. But carbs, lipids, and proteins are. And so we're going to put those together and figure out how that happens.